Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
All right, question 53 states that for part A, if each fission reaction of a uranium-235 nucleus releases about 2 times 10 to the 2 MeV of energy, determine the energy in joules released by the complete fissioning of 1 gram of uranium-235. Part B is different, so we'll just go through part A first. So part A, we're just asking, looking for the total amount of energy released in this reaction if the energy per reaction is given and we're given a mass. So in order to find the total energy, we can take the energy per reaction and multiply that by the number of reactions. So the number of reactions or number of atoms in a sample, we can use the relationship that this is equivalent to, N here is equivalent to the mass of your sample over the molar mass multiplied by Avogadro's number, which would give a complete number of atoms present, and we'll double check that with our units. But applying our values that we have currently, we have 2.0 times 10 to the 2 MeV per number of atoms here. We want our answer in joules, so I'll convert that now. 1.6 times 10 to the negative 13 joules per MeV. And then now this ratio, our mass, we're given to be 1 gram. The molar mass of uranium, 235.044 gram per mole. Multiplied by Avogadro's number, 6.022 times 10 to the 23 atoms, or we'll say, atoms per mole. So if all goes well, this should give us units of joules. So let's see, our MeV cancels out, our grams cancels out, 1 over moles cancels out, and number of atoms cancels out. The only unit we do have left is joules, as we hoped for. And we find to two significant figures that the amount of energy produced from fissioning 1 gram of uranium is 8.2 times 10 to the 10 joules. A huge amount. Part B of our question, how many grams of uranium-235 would be consumed in 1 year to supply the energy needs of a household that uses 30 kilowatt hours of energy per day on the average? So if this is the rate, the energy rate, I say P times T, power times time, because hour obviously is a time. So if we can determine the amount of energy produced in this scenario, this is P times T, but we need to convert a little bit of our units here. So if you have 30 kilowatt hours per day, kilowatt hour per day, it does ask, we want to know how much, how many grams will be consumed in 1 year. So we need to convert this to amount of energy in a year. So you know that there are 365 days per year. And we do want energy in joules, so we can convert that using 3.6 times 10 to the 6 joules per kilowatt hour. It's a conversion factor. We find the amount of energy per year, so maybe E per year, we'll say, per year, would be 3.94 times 10 to the 10 joules per year. So we can alternatively, actually from part 1, we can state that the value we have is the energy per mass or per gram, right? Because this whole thing was calculated using 1 gram of uranium. So if we call the energy per gram of uranium to be 8.2 times 10 to the 10, joules per gram, we could find, we're solving for mass of our system, or the mass needed to output this energy per year. in 1 year. So in this scenario, we'll also say energy equals energy per year times 1 year. So we need to worry about how much it is per year. We can simply say the energy over the energy per gram would give us mass. So by solving that, we would find, we'll notice that they both have units of 10 to the 10, so I'm going to ignore that. It would be 3.94 over 8.2. Again, everything has 10 to the 10, but they would cancel out. We find the amount of uranium-235 to power a house for a year would only be 0.48 grams. So a very small amount would be needed to produce that much power.